and his competitor, Awful Aim Adam, each have 3 arrows to fire at their targets. Naturally, Robin Hood hits the bullseye with each of his 3 shots, while his competitor's arrows hit the target all over the place. So who is more accurate? It's quite clear that Robin Hood is the more accurate archer, as all his arrows hit the bullseye. This works the same way as accuracy in science. The bullseye represents the true value of what we are trying to measure. The arrows are the experimental data we obtained. If our experimental method is accurate, like Robin Hood, then our results will be, in general, close to the true value. On the contrary, if we are inaccurate, like Awful Aim Adam, then our experimental values will be, overall, far away from the true value. Usually, we perform each step of our experimental method exactly as it's written down. Even so, our data can still be inaccurate. Why is that the case? This may be due to systematic errors. A systematic error is a repeated, reproducible error that is consistently in the same direction. To help understand what this means, let's go back to Robin Hood at the archery competition. This time, a strong crosswind is blowing to the left. Robin Hood still aims for the bullseye, but the wind blows each of his arrows to the left, so he always hits slightly left of the bullseye. This is a systematic error. Each time, the arrows are pushed in the same direction and are similar distances away from the true value. This systematic error has also made our data inaccurate, as our results have been pushed away from the true value, just like how the arrows have been blown away from the bullseye. But what gives us systematic errors in our experiments? Systematic errors are almost always a result of problems with how we have measured the value. That is, there is a problem with the instrument we are using to take the measurement, or there is a problem with the way in which we are using the instrument. For example, imagine you are measuring the mass of everyone in your class. However, when nothing is on the scale, it already has a reading of 2 kilograms. What will happen? Your results will show that everyone is 2 kilograms heavier than the true value of their mass. This systematic error exists because there is a problem with the instrument. The scale does not start at 0 kilograms, so of course it will not read the correct mass. As a result, there is a repeated error that causes everyone to appear heavier. If we reset the scales so that they start at 0, we can remove this systematic error, and everyone's mass will be measured correctly. Now imagine we are performing an experiment to measure the specific heat capacity of granite. This is the amount of thermal or heat energy needed to increase the temperature of 1 kilogram of granite by 1 degree Celsius. First, we pick a suitable sample, then measure its mass and its initial temperature. We heat the granite using an electric stove and measure its final temperature as 35 degrees Celsius. Next, your teacher brings out an infrared camera and accurately measures its temperature to be 70 degrees Celsius. Why are these numbers so different? When performing this experiment, you should be aware that granite is a very poor conductor. Even though it is quite warm, at 70 degrees Celsius, it does not readily transfer thermal energy to its surroundings. Thus, when measuring its temperature, the thermometer was not touching the granite sample for long enough and did not heat up to the true value of 70 degrees Celsius. Since we did not use the thermometer correctly, we have introduced a systematic error which rendered our experimental results inaccurate. To resolve this issue, you should allow sufficient time for the thermometer to reach thermal equilibrium with the granite sample, meaning that their temperatures are identical. You could also monitor the reading on the thermometer and wait until it stabilises to its final value. One of Robin Hood's competitors, Too Tall Trevor, faces a different dilemma. Too tall Trevor is simply too tall, and he makes the mistake of forgetting to adjust for his height when firing his arrow. So unfortunately, all of his arrows land above the bullseye. In this scenario, too tall Trevor's height introduces a systematic error. There is a repeated, reproducible error in a single direction. Let's quickly revise what we've learned so far. Accuracy is a measure of how close the experimental results are to the true value. Accuracy can be reduced by systematic errors, where there is a repeated error in the same direction. Systematic errors occur when there is a problem with the measuring instrument, or if we are using the instrument incorrectly. Let's go back to Too Tall Trevor, because Robin Hood is giving him some tips. What's this? Because Too Tall Trevor was landing all his arrows above the target, he could try to aim a little lower to reduce his systematic error and thus improve his accuracy. Genius! Similarly, there are ways that we can improve our accuracy when we perform experiments. Remember our first example where the measured mass of everyone in the class was too high because the scale started at 2 kilograms? When we readjusted the scales to start at 0, we removed our systematic error. This is known as calibration, which is a process where we readjust our measuring instruments against standards or accurate known values to ensure that they are measuring results accurately. When conducting experiments for the HSC physics course, you will need to know how to calibrate video software, which tracks the motion of objects, and a polarising filter, which only allows light waves at a certain angle to pass through. These processes are explained in Module 1, Kinematics, and Module 7, The Nature of Light. There are plenty of other instruments that require calibrating, including mass balancers, digital thermometers, and voltmeters. Another way to reduce systematic error is to ensure that we are using and reading our instrument correctly. An example of this is parallax error, which occurs when we read an instrument from an incorrect angle. Let's consider Thomson's experiment to measure the charge to mass ratio of an electron. In this case, a cathode ray, or beam of electrons, is travelling in a circle inside a glass tube. To measure the diameter of the circle, we need to place the ruler behind the apparatus, since we cannot open the glass chamber. To obtain measurements without parallax error, you should look perpendicular to the apparatus, using only one eye. If you are in the correct position, you should be able to see your eye and the cathode ray reflected in the metal ruler. Now, if you remain in the same position when taking the second measurement, you will be viewing the beam from an angle. Therefore, your measurement will be affected by parallax error, and your result will be inaccurate. To get the correct reading, you will need to move to a new position that is perpendicular to both the object and the ruler. The same principle applies when measuring the volume of water using a measuring cylinder. To obtain accurate measurements, you must read the bottom of the meniscus from eye level. Likewise, it is easy to make mistakes when constructing electrical circuits. Remember, you should always connect ammeters in series and voltmeters in parallel. Placing either a voltmeter or ammeter in the wrong location may cause the properties of the circuit to change drastically, leading to inaccurate measurements. If you'd like to understand why this occurs, watch our videos on voltmeters and ammeters in Module 4, Electricity and Magnetism. As you can see, accurate results can only be obtained if we use measuring devices correctly. The third method of reducing systematic errors is to reduce and measure the background noise levels. This is particularly important for experiments where you measure the intensity of light, sound, or radiation. Suppose we are performing an experiment to measure the amount of light emitted by a red LED. If you may recall, a lux meter is used to measure light intensity. Unfortunately, our measurements will be affected by light from our surroundings, such as light entering through windows or emitted from light bulbs. As a result, we will measure more light than what is emitted by the LED. To minimise the amount of stray light, we could perform the experiment underneath a thick blanket or in a dark room. We could also perform a background reading, that is, we can measure the intensity of stray light. The first value corresponds to the combined light intensity of the LED and the surroundings, while the second value corresponds to the surroundings only. Subtracting these two values gives us the light intensity of the LED, thus we obtain a result which is closer to the true value. These strategies can also be applied to experiments involving nuclear radiation. Imagine that we are trying to measure the amount of radiation produced by a sample of uranium. But there's a catch. Many objects around us are also radioactive. For instance, radiation originates from the ground, the sun, and outer space. Consequently, we will end up measuring the total amount of radiation from the uranium sample and the surrounding environment. This will lead to a result that is greater than the true value of the radiation emitted by the uranium sample in isolation. We can reduce the effect of background radiation on our results by shielding our measuring devices with lead, which readily absorbs radiation. Additionally, we could measure background radiation levels using instruments such as a Geiger counter, then subtract the background reading from our measurements. Let's consider experiments involving sound. If you don't have access to a soundproof room, then it's very difficult to eliminate background noise. You could measure the background noise levels, but this can change haphazardly, like when someone walks past or the class next door starts laughing. In this scenario, you could perform your experiment at a specific frequency. For example, you could connect a sine wave generator to a speaker and produce a pure 1000 Hz tone. After recording the sound, you could perform frequency analysis and isolate the peak at 1000 Hz. In doing this, you exclude sounds at other frequencies, such as cars driving past or people talking. By removing some of the background noise, you will be able to get more accurate results. One final method of minimising systematic errors is to reduce the amount of interactions between our experiment and the environment. This is particularly important in the topic thermodynamics, where you measure temperature changes and thermal or heat energy. Whenever we heat something up, it will lose thermal energy to the environment and cool down. Similarly, if we cool something down, it will gain thermal energy from the environment and warm up. Therefore, our measurements will demonstrate that hot objects are cooler than we expected, while cold objects are warmer than we intended. To avoid this problem, we can try to minimise the amount of thermal energy exchanged between our experiment and the environment. For example, we can perform experiments inside a styrofoam cup or calorimeter, which are both good insulators. Accuracy can also be affected by the resolution of instruments, which refers to how well the instrument can distinguish between two similar values. For example, let's look at this ant. If we use a 1 metre ruler with increments of 1 centimetre, we can say that the ant is around half a centimetre long. However, we can't be certain about the value since it lies somewhere between 0 and 1 centimetre. We cannot be certain that its length is exactly 0.5 centimetres as opposed to 0.53 or 0.51 centimetres. But if we use a 30 centimetre ruler with 1 millimetre increments, we can see that the ant is closest to 0.6 centimetres. Our measurement is now more accurate as the ruler with smaller increments allows us to obtain a number that is closer to the true value. Throughout the HSC physics course, you will encounter a range of measuring devices with different resolutions. For example, you could measure time intervals with a stopwatch, video cameras with different frame rates, or light gates. In general, you should try to use the most accurate instruments available while still being practical in the context of a school laboratory. Let's pause for a moment to look at the types of questions you could be asked in exams. Usually, you will be asked about accuracy in the context of a practical investigation. Questions will ask things such as, are the results accurate? Why are the results accurate or inaccurate? And how can we improve the accuracy of the results? The answers to each question will vary depending on which experiment you are asked about. If you would like to see how to answer these questions, please watch our videos for each of the practical investigations in the HSC course. Let's revise our understanding of this topic by looking at a sample question. Jeff is investigating the acceleration due to gravity using a swing at his local park. He is given the following material. Jeff measures the swing using the ruler. He cannot reach all the way to the top, so he has to stand on his toes and look at the ruler from an angle. He finds the swing to be 3.50 metres long. Next, he releases the swing at an angle of 20 degrees to the vertical and measures the time taken for 10 oscillations, or 10 complete swings. He repeats the experiment 3 times and calculates the average period for one swing to be 3.88 seconds. Which set of statements correctly describes the results from his experiment? Pause the video to think about your answer. Since this is quite a long multiple choice question, a good method of approach is to use the process of elimination. We will check each of the options, even if we think we already know the answer, and settle upon the most correct answer. Starting with option A, we know that stopwatches are very accurate as they have a high resolution, so the time taken for 10 oscillations were measured accurately. However, we cannot be certain that the results of this experiment are accurate based off this one small aspect. Since this experiment also involves measuring the length of the swing, we will have to consider whether it was accurately measured or not. So let's look at the other options and come back to this later. Option B describes repeating the experiment and taking an average. This is definitely an important thing to do, but it has no effect on the accuracy of the data. Remember, accuracy is about how the equipment is used and how the experiment is performed. Instead, taking an average improves the reliability of data, which refers to repeating experiments and obtaining similar results each time. As reliability does not affect accuracy, option B is incorrect. Now, option C claims that the results are inaccurate due to parallax error. As Jeff did not read the ruler at eye level, but rather from below, so there is a good chance that his measurement was smaller than the true value. Given the large distance between Jeff and the marking on the ruler, it is fair to claim that this systematic error is significant. Therefore, his results are inaccurate since the length of the swing was measured inaccurately. This also negates the possibility of option A being correct, as it claimed the results are accurate when they are not. We will keep this in mind as we assess option D. Option D describes the effect of human reaction time. The period of the pendulum may have been measured inaccurately, leading to inaccurate final results. This is plausible, so both options C and D appear to be correct. In spite of this, we need to find the most correct answer in the HSC exam, so we must determine whether parallax error or human reaction time is more significant. We can do this by calculating the percentage error due to both factors and comparing them. Remember, percentage error compares the experimental error to the true value by expressing it as a percentage. The experimental error is the difference between the true value and the measured value. Since Jeff was standing almost directly below the ruler when he measured the swing, we can estimate that the true value for the length of the swing is at least 20 centimetres greater than what he measured. So the true length of the swing would be around 3.7 metres, and the percentage error due to length would be approximately 5.4%. Next, the average period of the swing was 3.88 seconds. But since Jeff measured 10 oscillations, his stopwatch would have read 38.8 seconds. In comparison, the typical human reaction time is approximately 0.2 seconds. When performing the experiment, Jeff needed to make 2 measurements. He needed to press the stopwatch at the start and at the end of the 10 oscillations. Therefore, the total error in time would be around 0.4 seconds, and the percentage error due to reaction time is approximately 1%. Since the percentage error due to parallax error in measuring length is much greater than that due to Jeff's reaction time, we can conclude that the most correct answer is option C. Let's revise what we've discussed in this video. Accuracy is a measure of how close the experimental results are to the true value. Accuracy can be reduced by systematic errors. Accuracy is also limited by the resolution of instruments, which depends on the increments of your measuring device. Systematic errors are repeated, reproducible errors that are consistently in the same direction. We can reduce systematic errors by calibrating all measuring instruments, ensuring the instruments are used correctly, reducing and measuring background noise levels, and reducing any interactions with the environment. We hope you enjoyed this Schooling Online production. For more easy lessons on physics, check out our first video on reliability.